official welcome to year 2025, and I hope you will have a wonderful year, and I hope also you had a wonderful break and could I don't know, recover a little bit from all the tortures of 2024. It's been 2 weeks or so, and we've all forgotten what we did. So I'll remind you of the free real scalar field, also known as Klein-Gordon theory. So the classical Klein-Gordon equation we encountered very early as the first idea of relativistic quantum mechanics, and then we came up with Lagrangian. So let's write out the Lagrangian. That's this L thing. Half d mu phi d mu phi minus m squared minus a half m squared phi squared. So this is the theory, a real scalar field, and then there was this canonical way of guessing a consistent quantum theory based on the degrees of freedom of this field theory. And the idea was first to compute the canonically conjugate momentum density as the derivative of this L with respect to the time derivative of the field. Time derivative sits in this part, and you'll find phi dot, like the momentum. It is the momentum. And then the Hamiltonian or Hamiltonian density is the Legendre transformation of this L. That's defined as pi dot minus L, and if you do that, you'll find a half I squared plus a half, just the spatial derivatives of phi squared plus half m squared phi squared. So, and then you break, and then you write down the following relations for some operators actually on some Hilbert space. So we say I have an operator phi hat, and it depends on space. We fix time. That's a bit awkward somehow, but it's the procedure. You fix the time to some value. I don't write it as an argument. And then you have these operators dependent on space, and they are supposed to commute at different space-time points. And the pi's as well, they're operators for pi, x, and y. And if you have a mixture, say phi first, phi, then it's almost always zero, but not when they coincide. And these are the equal time commutation relations. And that's what they're supposed to satisfy. And you write down a Hamilton operator, which is just taking the Hamiltonian density, putting hats over everything. And then the normal H is the space integral over curly H. So it's a half I hat squared plus a half gradient squared plus a half m squared phi hat squared. And then there are equations of motion that tell you how to go away from this fixed time. It's the Heisenberg, that's the Hamilton, normal Hamilton equations, phi dot. Well, now at some point I have to include my time argument, maybe here. Now they become time dependent, and the time derivative at a certain time value is minus I phi commutated with H. This one. And that really works for all. Later, very soon, I'll say something about general operators, not just these fundamental fields. And then you have this evolution, time evolution equation for anything, things on time. change in time is equal to this commutator of that object with the Hamiltonian. So the same for pi, pi, pi. So that's that board is the basis of this real scalar quantum field theory. And what we did was then to see particles in all this business. And to see particles, you want creation annihilation operators. So we had to somehow turn these things into creation annihilation operators. How we did it was factorizing the Hamiltonian into a product, and then the two factors of the product were the creation annihilation operators. We could have done something different. We could have written down this equation of motion a little bit more general, and that in fact will turn out to be the normal, the classical Klein-Gordon equation. These two things, with the explicit H, will turn into that. And you know this as the classical equation of motion for this theory. We solved this equation explicitly using Fourier transformation. The solution looked like this. We did it when there were no hats there. So let's skip that for 1 second. Got E to phi. And let's also add the time, not just right now. One over E vector, this was convention. And then we had some integration constants A. That depends on P. Every P can have their own E to the, here is the I E vector X vector plus A complex conjugate E to the minus I P vector X vector. I'll mess with this equation a little bit. I'll put hats and I'll try to figure dagger in a second. So this was the general solution of this equation, the classical equation of motion. And these are the integration constants. If this field is supposed to be real, then they are not completely arbitrary. In fact, this is the complex conjugate of that there. The A's may be complex because they're complex I's hanging around, but there's a relation between these and these. And, so now instead of factorizing this thing, we could have done this ansatz for our quantum fields as well. Then these will be operators. It's the only place where you could have operators. I mean, this is the just functions. So if this is an operator, then just create become the operators. And then usually you don't write that. You write the proper dagger for this thing. So we could have just said, well, we know this from the classical theory, and we know that these Hamilton equation of motion are the same for the quantum theory. So that is probably a good answer, because these things are constants, integration constants. And so plug this in there, and then we see what we get. I mean, there wasn't really a guarantee that we find the creation annihilation operators, but this is pretty much guaranteed. This expansion makes some sense. And then you could later find what these commutation relations imply for the A's. So either this or the other way, these guys are operators satisfying this thing here. A P with A dagger Q is equal to 2 pi Q. This is just because of Fourier transform. And then we have a delta C P minus P. And A with A and A dagger is 0. And then we are happy because then we see, these A's are like ladder operators, and there is a number operator associated with them. So number operator like if you have a dagger P, A, P, and you probably want to integrate over all the P's. Let's write it. Let me not state. P, I, U, and then we have learned that this no root is the source of integration measure with a dagger P, A, P. So this is a number operator. And the a dagger raises this number. I'm just going to give it a name. I'm not going to. And the a without the dagger lowers it. So having this as a consequence of this means that we have these ladder operators, but there was still no guarantee that this is somehow the Hamiltonian, but it was happily. So H is just this number operator with without this fact, actually with this thing in the numerator. So it's without this factor, H is without this factor, but you want this factor to have it Lorentz invariant, and then if it's without, you have to put it in the numerator to cancel it. So this is integral d3 p 2 pi cubed 1 over 2 p, and then the 2 goes away because when you really plug it in, you get both terms. And so the 2 goes away. So there's this 2 and then there's the 2. Then I'm getting confused with my normalizations. There's this A and there's the alpha. Do I have it in my notes? Do you have it in your head? We should all know our Hamiltonian, right? So in terms of the A, there's no, there's just there's the numerator, in fact. So there's this thing isn't there. It's ET with a half. If you have both terms, if you've already turned one around, then it is this thing. So it was really plus an infinite constant. You look like you're confirming it. Have you confirmed?
I haven't yet.
Oh, but yeah, that's the thing. So this thing counts how many excitations you have in a state. When this acts on a state, this counts how many interactions, excitations you have with a certain p, and this takes care of all the p's, and then you sum their energies. So it's a very nice Hamiltonian. And this was this annoying infinite constant, which, yeah, basically counts the ground state energy of all the different modes of P. And since we only care about the difference between one state, the energy in one state and another state, this infinite ground state energy isn't really super important because all the states have this shift. And then you usually ignore this thing and you call this H prime, and then you don't want to write prime anymore, so you call this thing H. That's the main part of the story. We have talked about the scalar field for a long time. For example, adding the time into this, like what is the field phi for arbitrary times? So phi of x, where this x is now the 4 vector t and x vector, hat, and it just added a phase, an extra phase, and it could be written in a very nice way over square root 2 e to the minus I t x. These things have error on top. This is just the 3 part. This is the 4 vector and the scalar product. So this is the same as there minus energy times time, minus I energy times time, plus a dagger e to the I, the x different sign, and done. So this is now the field for arbitrary times. And then we wanted to know, so what happens when we commute fields, for example, them here for different times, not at equal times. That's the question of microcausality. So this is my picture, space and time. Then I have in all these locations, one of these operators, right? This x without an error is a combination of x and t. So I have an operator here, and you can have another operator there, and not at the same slice. And do they commute or not? Different operators, we don't know. And then we discuss this. And found, actually this had a name. This thing had the name delta x and y, defined as the commutator, x and y. And that's something, in general, it's a, you can write down in terms of another integral. So I write it, I think I want to write it. You plug this in, and then you find this d x minus y minus d y minus x, where d of some argument x, so x minus y, is integral d3 d2 pi cubed 1 over square root 2 e to the minus I p. So this integral here, x minus y, and the p0 is e p. So you have to insert this stuff now, and we did this, and then you go through it, and you find two terms that look like this, which come from, well, the cross terms, this with this from the other, and so on. We did this, and this is just a shorthand. D is the shorthand, and then the result is the difference of the two d's. And you can actually, they are also this, the vacuum expectation value of the product of two phi. So this d, the single one, is this. And we said that that is the closest we can have to a position eigenstate. So this is something at location y, and this is some at location x, and this kind of creates it at x, and then you ask what's the overlap. This creates it at y0 at location y, and this at x is asked what is it at time x0 at location x. And so that's what we call the propagator. It propagates from one time to another time, from one location to another location. So not here in this picture, if you want. So this is the kind of the propagator. This words, and this commutator is the difference. But you can't just turn these things around. So this is not equal to this. It's not symmetric. It's not the symmetric function, although it almost looks like it. Because if you turn this around, you get a minus sign here. So this minus sign gets eaten, and you have a plus. But you think you could put this back in by changing the integration constant from p here to minus p, then introduce it again. But it doesn't do this for the time part. So the time part, the p0 is so e of minus p is e of p. So that doesn't change the time. So it really isn't symmetric. But it is Lorentz invariant, this thing, with all these factors as we discussed. And so if you found a Lorentz transformation to another argument, well, So the d of lambda sum x is equal to d of x. So you can just take in the Lorentz transformation. If you found a Lorentz transformation which turns the difference y minus x into x minus y, then these two things are equal and cancel. And you can find such a Lorentz transformation if the difference x minus y is space-like. So here, try to draw this space-like. Everything that is outside the light cone is space-like, and then the two terms cancel, and then you get 0 for x minus y squared less than 0. It's called space-like. So if they are so far apart that they shouldn't talk to each other, then the commutator is really 0. It's called microcausality. And so that's for the first, but you could also take the time derivative of this and then you find that this is 0, or you take the time derivative, sorry, time derivative of both and you find this is 0, or the time derivative of this. And then that's 0. If they're spacely apart, then they can never be equal. Now these were some more discussions. I guess this is all the reminder that I want to give you. You have discussed in your homework more of these like D functions, like higher point correlation functions. Have you done this yet? It was fun. And then also you looked at the complex scalar field, and it's similar, just a little more complicated. The interesting addition is that you have two different types of excitations. You have an A and an independent B, because you don't have to require anymore that this is the complex conjugate of this. So they are really independent thing. The energy, or the Hamiltonian, is just the sum of the excitations of A type and B type. But you have another conserved charge, another Noether charge, related to the phase rotation of this. So if you rotate phi, then that's a symmetry. If you rotate the phase, so phi goes to e to the I alpha phi, that in the complex theory, where one of them is complex conjugated, is a symmetry, and then you have another charge, Q, and that also looks like this, doesn't have this E factor, but a different relative sign. So one of the two have a positive charge Q, and other have negative charge Q, and these are the opposite interparty to each other. Enough reminder? You reminded enough? Good. Then I have a little bit more a formal discussion about the Heisenberg picture and the Schrödinger picture to sort this out. This is something general, but I do it in the context of the scalar field. Then we're done with the scalar field, and this week is the Dirac spinor. And I reminded you of this because this will be super similar, and it's good to have these charges and you have these operators, of course. It's just a little bit more complicated because of an extra index floating on. So, but before, let's talk about this Heisenberg versus Schrödinger picture. You know this from ordinary quantum mechanics, but I still want to recall it here. We won't put it to use immediately. It'll be very important when we move to interactions. I'll also discuss why. Then it gets even more complicated because it's the third picture, the Dirac picture. So let's just sort this out at this point. What are we talking about? So these are the operators. Maybe we take one that is actually time dependent, this one. So they are normally time dependent. And I said here, this is the evolution equation. So let's say I have some operator. A depends on, in particular on time. And that could be some function of my fundamental fields. Derivatives of it, if you want. So just, I'm writing this so that you know what do I know. So it could be one of them, or it could be a function, it could be lots of things. So this is now an operator, and it evolves according to this equation there. So I have a dot, and that finds I a x, and then the Hamiltonian of this here. So the operators change in time. My states that we built, they don't. So the states that we created, say out of these, for example, a dagger, t, la la la. So these things, there's no time, right? They well, it could be well be that this is the state at a certain time. But what I really want, what I would say, we don't let the states change ever here. So let's not confuse ourselves with this example. So the states, as we've been discussing here, are time dependent, are time independent. So some operator, what does it sum mean? So far, operators are time dependent. So that makes more sense. So far, in our discussion so far, our operators, and to be listing, are time dependent, that's how they change. And the states, so far, are time independent, and it's just right the next side. And you should, well, you should think of the state and its name as describing the system that you have at the certain time. So, for example, as the initial conditions, you'd say, oh, when I started this morning, I had two particles with momentum p, and then this is the state, and it's constant. It will, well, there will be a time evolution of, say, where things are, of expectation values, but you say, you want to say what you have prepared, you'll just give the name of what describes the system at your reference time. So you say I have two particles with momenta P1 and P2, say. And that's the state, and that's what it is, time independent. It just describes how this thing is set up. And if they do what they do, this is all determined. There's this time evolution thing. But this is how you call, let's say, you make the state time independent. And the expectation values are possibly time dependent because the operators that you stick into these between two things, so between psi and chi, say, they have the t in here. It's right, the t explicit. I really care about the t, not the x. I mean, it could even be non-local and more x. I do care about the t. Remove the x's. No. So, and that's now a function of t, and it tells me what the expectation value of phase. And this way of doing it is called Heisenberg picture. And it some people say it's closer to classical mechanics than the other picture. And so you think of this could be the position operator, like and then that changes, like the position changes of a particle. So now the position operator changes. And this thing is the more like the initial condition. It says where did you start? And then the expectation value here changes in the time evolution is carried by this operator. Doesn't really matter, but this is how people say this is closer to classical mechanics, and this is one way of thinking it, and that's the way that came out of this. It is not the way that you learn quantum mechanics at first. Quantum mechanics, you hear something different. You have a state that is time dependent. You give an initial state, and then you have the Schrödinger equation that evolves. And now this is not a different thing. It's just, well, it's not fundamentally different. It's just a different way of writing it down. And here comes the relation. In order not to get confused, all these operators and states get a little index for the purpose of the section. So this is the H for Heisenberg. This is the Heisenberg operator, and it satisfies the Heisenberg. Well, this equation, the Heisenberg operator satisfies the Hamilton equation of motion, and these are the Heisenberg states. And then you have that. And now you want to move the time depends from the state to the states. So I can just write psi h a of c and x pi h, and I want psi now of t s, and then I have an a s, and that's just x, doesn't change in time, and then pi of t and s. I have to figure out what they are. The s, the as of x, I just defined as the Hamilton at a certain reference time. Shall we say 0 or t0? Well, you make it more complicated. I'll just say 0. This is the reference time for simplicity. 0. If you want 1, you use 1 second. That's also possible. And then that's my definition. Can we figure out what this what's happening now? So here, this goes there. So here I have the t, and I want really to have a 0 there, but I still want to have it equal, so I have to kind of extract the time dependence. That means I have to solve this equation, but we are used to solve this last year, and so this a, this can really, if the h is time independent, this can simply be solved, and then we have h of t and x is equal to e to the, yeah, and now don't do it with the sign. You figure out the sign h and t. If you have, well, then it comes 0. If we had chosen a different time than 0, we would have to subtract our 2 seconds or so here, and then there's a t to I h t. And now we have to figure out this there minus sign, and there's a minus sign. How? I guess plugging it in. Painful. So I'm differentiating this object. Boom. Then this comes down as IH on the left, and we have the H there. So when the H is on the left, I want the, oh, that works. Right, if it's on the left, the other part in the complicator, I want the plus. So it's this way. So this minus is great, and that's bad. And now it's all good. And if I insert that guy there, and here, I can see that psi h, or let's use the other way around, this guy, the chi h has to be whatever's on the right, e to the minus I h t chi t s. Or really, let's take this to the other side, and we have chi t Schrödinger is I don't like the sign now. Let's take it to the other side and complain about the set sign in a minute. Chi H, and chi H. Yeah, well, that's what it is. That's the relation. Although I don't like the sign, I really want. Well, do you want the minus? Isn't the yeah? It's a minus there. Damn it! Why is this not working? Differentiating, and this comes down in front. Behind. So something's really sad. See what we did. This thing sits in there, and I just tried to do 100 steps in one. I plug this in there, and then next to him is this factor. So it is e to the minus IHT, huh? That's on this side, and on the other side is my Schrödinger. So it is already there. And now 2025 can start really well. So this is my Schrödinger state. It is related to this Heisenberg state by this guy. We could also just for fun insert the reference time. So if I put a 0 here, then there's a 0, and then this all goes away. So the Heisenberg state is really the Schrödinger state at reference time. So if I do this, then I get the same equation here, the Schrödinger state at 0. And now you've seen this probably. This is just a time evolution of this, and that state satisfies Schrödinger's equation. Schrödinger's equation. So we could, for fun, just differentiate this thing. Chi of t s d by dt, and then I get a minus I h, and this thing again, minus I h t chi 0 s, but this is the state at time t again. This is chi t s. Let's take the I on to the other side. So I is by d by dt chi t s is h psi chi t s. There's your well known Schrödinger equation. So that's the relation, just this unitary transformation from one unitary time dependent transformation. Either you make the states time dependent or the operators. We came now naturally from the time dependent operators, but I wanted to connect it to what you know, quantum mechanics where the state is. And yeah, before I'm commenting on the interactions, let's maybe see how the states in this Schrödinger picture transform in this Klein-Gordon theory. They will transform trivially, but let's still say it. So time evolution of states in this Klein-Gordon theory in the Schrödinger picture talk is fine. So we have say what do we have? We have let's just write it. This is the A dagger V1, A dagger V2, and so on the vacuum. And how does this change in time? Well, you have to multiply the Hamilton, the time relation to the Hamilton operator in front. And then what we get is simple, like we know what the commutator, yeah, we know what the commutator h with a is, and the exponential in front with a, and the similar exponential in the back, like no space. So e to the minus I h t a dagger t e to the I h t. We did this computation earlier when we tried to figure out the time dependence of our scalar field, and we got e to the minus I e related to this p t a dagger p. So we can use this here if we stick between all these raising operators in color yellow. Here, e to the plus I h t, e to the minus I h t. So it's just an identity. And these three factors together make one exponential, e to the minus I e 1 t, and then so this is gone, and then we have a similar expression just shifted one particle to the right. And then we do this for the second particle and so on. So we get the sum e to the 2 plus times 3 plus, if there's more, and then the same state. A E1, A E2. So that's the state, the initial state. The initial state multiplied by the time evolution is the state at a later time. So that's the state at a later time, but the state at a later time is the state, the initial state times this phase, which doesn't really matter much. Yes?
Wouldn't we get like one, like h e to the I h t remaining? Like if we then
Yes.
plug in more.
You're very, very good, very observant. So we have e to the minus I h t remaining.
I see.
Stole that. But now, yeah, we can actually apply this h, and if there's no vacuum energy, then this will kill them. So expand this, it's 1 minus I h t minus whatever I half I squared 2 factorial h squared t squared and so on. And all the h's kill this thing. And you have only the one left. Yes. I didn't say that. So very good. Yeah. It measures, this guy just measures the energy of everything. And that has energy 0, but 0 in the exponent, so e to the 0. It doesn't kill everything totally, but it just kills the exponent. Very good, thanks. So the time evolution of these states that we so proudly discovered in this theory, right? They evolve very trivially. And if you wanted to know at a later state, at a later point in time, what's the particle content of your system when you prepared it in a certain way, the answer it'll be exactly the same thing, because these states are all also not orthogonal to each other. So at a later point, you still have these number of particles with exactly these momenta. And that holds for any time t. So all the time, always the same particles with the same momenta, you would call that theory free. Didn't I write this? Free real scalar field. So that's what we have. We have just a bunch of particles, and if you consider a state, then it just goes. Now, I guess I'm going to say now. Now, at some point, we will want to have something more exciting where things come in, scatter, and then come out again. And so we have to add, in fact, in 2 weeks from now, we'll add the interactions. And that makes things very different. So we had the Lagrangian that was roughly b phi squared minus m phi squared. And now we're going to add some stuff. The simplest thing you can add is phi to the 4. You could add phi to the 3, but that doesn't have a unique sign. Actually, I think you want to add a minus phi. So if you have cubed, then depending on the sign of phi, you can have either thing. It doesn't look like bounded already. So the simplest is to the 4. But now your equation of motion will look roughly, so this is also roughly like what we had before. Linear, non-linear, phi cubed. And then I ask you one exercise, find the general solution to this equation. And it was simple in this case, here 0, but here it's just impossible, I guess, right? To this nonlinear partial differential equation, good luck. And so then we'll, all the remaining, I guess, 8 weeks, counted them, we'll have to deal with this. But you see the problem, if our quantum field satisfies this, then the quantum field won't have this nice expansion in terms of A's and A daggers. Because it's a different field, it doesn't work anymore. And then the work starts, and then we have to introduce this in-between picture, the Dirac picture, or also called interaction picture because it works for the interactions, and then split the job between the operators and the states. Then we'll arrange it such that the operators get only the trivial time dependence, and then all what we worked is still valid, and then we get the remaining part to the states and see what we can do there. So this is the preview. Right. So now the idea is, rather than jumping into this complication, repeat the whole story in a slightly different or slightly more complicated setting with a Dirac spinner for this week, and then for next week, I was going to say even more complicated for the vector, but it's just different. It's not more complicated. I mean, spinners are pretty awful already. This 6.2, 3, so the boring, Dirac spinner field. And I quite like that we discussed this now because we can see all the steps again. And we're basing this, this is now based on the psi, on the Lagrangian psi bar I d slash minus m psi. I hope you remember everything. So psi is what? Psi is not a scalar field because it's called a spinner. What does it mean? And what does that really mean? Oh yeah, that's complicated. What here?
On the left and right, while
Yeah, so exactly. So two components. It means that we have 4 components. It's just the thing with some components. It does transform under complicated representation of the Lorentz group, but it is something that has more components than just one. And I want to introduce now a label because sometimes I'll need it. So far, we have written this in terms of like index-free notation, but they are, as a matter of fact, multi-component things. They are 4-component objects, and you say the left and right component if you take it a while. So the A labels these spinner components. And just to understand this from the spinner index point of view, let's spell it out. So the D slash is by definition a gamma matrix, U times whatever this vector is that you flash through. So this is a matrix in the spinor space. So this has, because the matrix has two indices. So this thing then has two indices, and that would look like psi bar A, B slash AB, and then psi B. Here, I'm not doing anything fancy with upper and lower indices. Let's just keep them all lower. There's no metric. You could go really crazy, and it's from the Werden notation where you have the epsilon as a tensor, but then you have to split this 4 into 2 and 2. You're not why, right? They're all downstairs, and this is a matrix product. Now, this is a matrix with a scalar, sorry, matrix with a the vector, like a column, a matrix with a column, and then this row with that column that you get from here. And what do we do with the M? Well, the M is pretty lonely here. The M is not even a matrix. But it better be a matrix if you, so what do we do with the M? If you want to, yeah, let's do that. So then if the notation should make any sense, then we have to write this. So there's this secret delta. That's why I wanted to write it. It could be confusing at first, but yeah, that's what I said. Now, if you just copy what we've done here, we would compute the momentum conjugate. So we go pi, and then let's do it. So pi is by definition dl by d. Yeah, see, I didn't want that now. By dot. Let's just sketch it. There will be more words. So we would do this derivative, then we would do the Hamiltonian, and then we would have the here, these guys, psi with pi. By the way, this is also something, but there's many indices, right? So we do this for every of the spinor components. So this is also a spinor. Momentum density spinor, I guess. And then the commutation relations would be something like this: psi a x vector pi b y vector equals I, and then it should be probably diagonal, like only the momentum conjugate to its own field. So when the index is the same, should have a non-trivial commutator, delta 3x vector minus y vector. I'm also going to mess with this equation in case you copy, but you all copy digitally. You can also easily erase. Well, hat. That's what you would do. And then you would get very far. You would find oscillators. You'd find a Hamiltonian. You could find the charge, their charge is a charge field. You can find the Q operator, and you can confirm the microcausality even. And it's all very good, except that the Hamiltonian will have an unbounded spectrum. And then you start to go back. See, this unbounded spectrum, so what does it mean? It means you have states with arbitrarily low energy. There's no state with the lowest, with a lowest finite energy. This is unbounded. So, and if this happens, you'd say, okay, so what? Yes?
Me. No, never mind. Sorry.
But don't forget the question. And it comes back. So if this happens, then at first in this free theory, no problem, right? You prepare 12 particles, and they'll remain 12 particles because they're free. Nothing happens. There's no problem that there is also another state of infinitely low energy because you don't have that. You don't care about the things that you don't have prepared. So it's not so bad. But when you introduce interactions, then they are not conserved anymore, those particles, and then they can decay. And then if you have something infinitely low in energy available, it's just going to go downhill. Yeah.
Is that the reason why we have to say that they anti-commute with each other?
And that's the only way out, really. So let's I'm going to do the computation, but let's sketch this fact here, I guess, for a second. So the Hamiltonian, so this is a sketch, don't copy, sketch. H will turn out, I haven't even written down what H is classically, but it will turn out to be a combination like for the scalar field. It will have a string component as another index. Actually, you've seen the classical solution, so I don't need to be so secretive. There's this S thing, and then there's A, S, T, and then there's minus B, S, T, B, dagger, S, P. Right. And here we have the integral over P and the sum over S. So this is how this roughly looks like when you go through this program, this standard program, what we did for the classical field. And it really all looks good. And then you start thinking about the sign, and it means the particles that are created with this thing are, so first, yeah. First you think, oh, wait a minute. Here's no dagger, there's opposite order. So let's just, why did I write it this way? I skipped all the computation, but I wrote this, which doesn't seem to be the final result. I wrote this line because up to here, you haven't changed the order of anything. So here, this is completely agnostic with respect to how they change. So this could be anything yet. Now, if you went for the commutator thing, you'd commute them around, then this dagger moves here, you get an infinite constant, we have never really had trouble killing that. So then it moved there, and now we have two proper number operators there. But since there's a relative sign, we could change this overall sign by redefining what the charge is, but the relative sign we won't can't get rid of. So one contributes with one sign to H and one to the other, so one positive or negative, and therefore it's in both directions unbounded. If it was only to the bottom, we just put a minus sign up front and turn the spectrum upside down. But since we have both signs, that's bad. And yeah, you now you come up with all these ideas. Let's redefine them. Right? Put a minus sign. That's B goes to minus B. Doesn't help because this has another minus sign. If you put in I, doesn't help because this is the dagger and so on. Yes.
Wouldn't we have a problem anyway for for defining the creation and annihilation operators if we have an unbounded spectrum? Because like always when we argued that like okay, these are all of our states can be created by these things, then like we always use at some point, okay, there's a lowest state of energy, so like I don't know, there's only one ladder, and
but before we said that there's a lowest and only one ladder, we said if there is some state with a certain energy, then this one will be the state with whatever that adds the energy to it. So this doesn't need the lowest thing. So you have the steps.
Okay.
But it goes down.
But we might have like a second ladder.
Yes, you might have a second ladder.
This doesn't interact with that.
Yeah.
Okay.
Right. But we still have these steps there. And this goes down. So redefining nothing helps. But what helps is since this is here, and now we say if they didn't commute but anti-commuted, then I turn them around. So then this is B dagger S P, so minus basically, and B S P plus our infinite constant, so that's no problem, but we have gotten rid of that sign. So then that works. Okay, in fact, there are books Pascal Schroeder is a book who does that, who wants you to see how far you can actually go with the commutation relations and like many pages. And then he says, okay, now I have to give up and do it one more time. In fact, what happened to me was like, if you don't read it, you just want to look up something, you go and you don't look in the table of contents, you just go and find the formulas you want, and then you found something with fermions, and you copy it, and then you happened later, you find, oh, you were in a section how not to quantize it. So it's that long, so you can go really, really far with it. But now let's think before we do all this computation. In the single particle case, the Dirac equation, you know from the relativistic description of, say, atoms, hydrogen atoms, then it's the description of the equation for the electron, say, with relativistic correction. And the electron, well, they've said it, but we've heard it. It's the spin 1/2 particle. The spin half integer particles are fermions, with that means they satisfy this Pauli exclusion principle. Otherwise, our atoms wouldn't even work, right? So if you put all the electrons there, then there's not much chemistry going on. So we know that there's something that forbids two exciting twice the same thing. Boson's fine, but here no. And how do you do this? Well, by having anti-commuting creation oscillators. We had this in the problem set. So if you want states that are antisymmetric in your particles, and if they're antisymmetric, then the two things can't have the same value. If index I and j are antisymmetrized, then I and j can't both be 1, because then it's 0. So antisymmetry, one thing. And if they anti-commute, then it's exactly what you get. So we are not surprised anymore. And thirdly, when we wrote down, when we discussed the Weil spinners, here, these guys, and we wanted to add a mass term to it. We had this Majorana mass term. And the equation of motion was fine. The equation of motion had this, and then we had the psi star in there, because one had a sigma, and the other with the d, and the other one didn't, and so they all transformed fine. We had to have psi and psi always conjugate, and now the equation of motion was good, but to write a Lagrangian for this, we had to suddenly pull the Grassmann valued field out of the head, out of the hat, yes. Stein, wherever, pull it. And then Grassmann field, anti-commuting. Well, any reasonable person at that point would have said, it just tries to tell us that there are no Majorana fields in nature, right? It just doesn't work mathematically, so it's probably just telling us that no, it just forecasts this thing here. So the Dirac spinner, which is made out of these Weil spinners, it wants to be antisymmetric. Good. So now we kind of accept this and now do the real derivation rather than going all through the wrong one. And we have motivation enough for doing this. So now here, the classical fields are Grassmann fields and they anti-commute. And now, if I want to define a pi, I have to tell you, differentiate with respect from left or right. That's why I hesitated here before. So this doesn't really make sense if I say from where, and I write from R, because then it almost will be, like Taylor's mentioned, we're nicer if you differentiate from R. So the pi is this is from R. Good. And here we'll have anti-commutators. This is what we want. So where's the time derivative? The L is psi bar. Well, really, it's psi dagger gamma 0, because bar is dagger and gamma 0. And then we have here I gamma 0 gt my plus I got no vector, so minus from the metric vector times gradient minus m psi. So the time derivative is here. So it is really psi dagger, I, psi dagger, psi dot, plus other non-time derivative things. And if I come with this derivative from the right, it just feeds this and this is left. So pi a x is I psi dagger x. That's the conjugate momentum. Same I here. A here. A just straight contracted. Or you leave it out. Now you say, oh my God, that also looks weird. I don't even have a time derivative. What momentum doesn't have time? You know, every momentum. Do you know what momentum is? E is mv or x dot. There is always coordinate time derivative, and we had it here for the scalar field. It was phi dot, wasn't it? And now there isn't. So our commutation relation here, if these now turn into operators, let's just do this now, quantize, la la la, then we have psi a x with psi dagger b y. Well, there's an I, so let's give us the I. Let's not give us the I and kill this I. Delta a b delta 3 x minus y. So this is what we have. It isn't like before. It's it's not psi dot. It's just unusual, but it's nothing bad yet. In fact, it won't ever be bad. It's just unusual. I want to point it out. And the next thing is we learned if this is a complex field, so this is complex as phi, psi, and psi dagger. Then you also have the other equation of motion, right? You have two degrees of freedom, the real and imaginary part, or the field in its complex conjugate. But the complex conjugate doesn't appear here with a time derivative. So so basically this thing, the momentum to the psi dagger isn't there. There's nothing. It doesn't. So the psi dagger doesn't have a conjugate momentum. But as you say here, the psi dagger is the conjugate momentum of the field. So they are coordinated to each other. And here so it looks like psi A next, psi B Y is 0, and dagger with dagger. It's also 0. Everything they have dagger with dagger. And this is how the system looks like. We have operators. They have 4 components. They are complex. We have psi and psi dagger, and they anticommute like this. The I that used to be there is gone because this is really the moment here. This I has been eaten. And the Hamiltonian H is now this pi psi dot minus L. But this was I psi dagger psi dot minus all of this. And the first thing is I psi dagger psi, and then I better, why didn't I write it? So minus psi, let's put this back to be bar I gamma vector times this minus plus m psi. Right? So this is the L. I extracted the first term because now I can see that these cancel. Our Hamiltonian is psi bar I gamma times now plus m psi. Classical one, and then hats on it, and then it's the quantum one. Alright. What about the equations of motion? These Hamilton equation of motion, psi dot of t and x should be something like minus I psi t and x and this h. What am I going to put around? So obviously, right, you'd think we will go all the way, right? If you have, don't write, if you want to go all the way, every commutator is now from now on be an anti-commutator whatsoever. No, this h is quadratic in size. So it's quadratic in Grassmann field. And if you have two, if you move another Grassmann guy through two other Grassmanns, you get a minus sign from the first switch and another minus sign from the second switch. So two of them, minus is plus. So then the h itself is what they call Grassmann even. So here, nothing weird. That's the constant remains. Interesting, huh? And well, dagger, that's the dagger. It even works. If you put the dagger here, then you get dagger, dagger, but you also have to turn them around and you get a minus sign from here. This is Hermitian. You turn this back, which brings the minus sign back, and then you have the same looking equation just with the dagger. So everything's beautiful. And what is this equation? What is the time, by the way? I want to know what this equation. Let's do this for fun and insert. This is going to be our first computation with Dirac quantum field. So the h from there, this is the normal h, straight h. So there's a space integral. So it's an integral over d. The x is already solved, so it's a d tried 3y. And then comes psi bar. I think I want, because we only know dagger, I want to go back to dagger, then the gamma 0 is explicit. And then we have I gamma vector times this is also yeah, whatever. This thing plus m psi. So this is derivative with respect to y because this is a field y. And it depends on t. It's an operator, and it's an operator. And like this, like this. I just inserted this thing. And I wrote the bar explicitly the dagger gamma 0 because now I want to use the commutation, or rather anti-commutation relations to simplify this. So I have a commutator, and I don't know what the commutator between the fields are, but I know the anti-commutator, so I have to be clever, and you know that A with B, C is A, B anti-commutator, C minus B, A, C. If you spell the right hand side out, both sides out, then you'll see that it works. So ABC is here, and the BCA is BCA here, and the other two cancel. So that's what I'm going to use here. So this is equal minus I. Now, this is the A. We have an integral d through y in this business, and then psi 3 and x. And then the b is the first factor, and the first factor I is that, and the second factor is this. And then there's stuff in the middle. And now I have to do something with the indices. This is getting confusing. The best thing is to also give this guy an index in yellow. So this is A, and then this is A, and this is A. And here That's the A. Now I want the first one. That's psi, dagger, T and Y, and let's give this the index B. And then what's outside is contracted with this B, so it gets big parentheses B. And inside we write gamma 0, I, gamma vector, Y plus M psi D Y, right? So that's the first term. It was all in there, but then I pulled the C out. Then I have an anti-commutator, and this really does talk to this guy. Now, continuing the same expression, this is going to be a plus now. But there's not going to be a plus, there's a minus sign, minus. And now the B goes first. The B is psi dagger T Y multiplying gamma 0 I gamma vector gradient Y plus M. All of this has an index. Well, it can't have A. It's going to have B, I suppose. B. Then what's called A here? Let's try A to X. And then the C is the psi to Y. And this contracts here. And now like this. Does this make any sense? And what would you like to do now? Exactly, and we happily find that this is 0. So much work for nothing. And this is delta AB, and then delta 3x minus y. And so we use this delta function to integrate over y. And it sets y to, yes?
Didn't you swap around in the second line it looks different from what I thought it should be. Like, shouldn't we take psi A Tx anti-commutating with this big thing in the brackets? Like, is this our C?
This is the C, this is the B, and this is the A.
Okay, I see.
And then there's this middle thing, which is probably D, and that didn't appear. This goes in the middle where we.
Okay, we can, okay.
No, but I could have known from the start that this and this doesn't give me anything because psi and psi anti-commute, but I wanted to see it. It's our first computation altogether. Now equals minus I delta AB, and then gamma 0 I gamma vector times gradient or nabla plus M psi, and this is now X because of the integration. In fact, I can use this. Well, this was now B. Let's do it. This was B, and then delta AB with this B, it just turns the B into an A. And if I write the equation again without indices, so psi dot, because both has an A now, left and right, it's needing X. Is equal minus I gamma 0 I gamma vector blah blah plus M psi 3x. So I left out the indices because it's both sides have the same. So I can use this index 3 notation and clean it up a little bit by multiplying from the left with I gamma 0, then this minus I goes away, gamma 0 squares to 1. So I have I gamma 0 psi dot equals I gamma vector plus m psi in argument. And you recognize this combination, bring this to the other side, combine it. So let's bring this to the side. And then we have, this is really I e sketch minus m psi hat equals 0. Surprise. Surprise. This is the classical equation of motion here. Same, just with a hat on it. So the quantum field satisfies the same equation as the classical field. Who cares about the classical field? This is now our equation. Here, this is the one we postulated. We use the anti-commutators, we use the Hamiltonian that we had there, and we get the equation of motion. I mean, how lucky are we today? What's next? We want to find the particles of the theory. We want to find creation and relation operators. I did say something, I gave this sketch a preview and I said there were some. How do you find them? Now we could, early in the beginning of this lecture, I said the two ways. Either we factorize the Hamiltonian, we just stare at this thing and try to guess what it is, or since we have already found the general solution to this equation without the hat, and this is the same equation, you can just use it and plug it in. And then whatever, let's do this here. Whatever they satisfy, this is what it is. And if they are not number operators, then they aren't. You can't force anybody. So we use psi. I think I'm going to write it without. I'm going to change it. So this is the reminder of how it looked like. In fact, there we could have we gave already the full time dependent one. So let's write this. It's integral d3p 2 pi cube 1 over 2 and then there were these a with the sums. We have two degrees of freedom, a s p vector, and then there was this wave function u s of p e to the minus I x 4 vectors plus b dagger s p vector. Oh, these are hats now. Okay, well, so for the operator v, the other wave function for the negative frequency ones, e to the I x. And the T0 is positive energy. Yes. So without the hats, this is the solution we had. Now we make this ansatz and use it. And we know it solves that equation. And the pi is what was it? Pi was I psi dagger. So it's I, yes, I into d3p 2 pi cubed I square root 2 e sum s1 2, and then the dagger. And if it changes this sign, I want this term front. B s p v dagger s e to the minus I x plus a dagger s u dagger s e to the minus plus I x boom. So here they are. And what we should do now in 5 minutes, what we should do now is invert these relations. So find the A and B's in terms of psi and pi. And then, when we have that, we can ask what is A P S with AR Q? Most interestingly, this. You can just ask, what is it? And what you would find is 2 pi cubed delta delta 3 p minus q. So exactly what we want that you will find. But this computation, and for the b's as well, and everything on 0, but the computation is very lengthy, too long for 5 minutes. So that's why I gave this as a homework. It is with a guide how to invert it. It's basically the inverse Fourier transform. It's just a bit annoying. There's 2 terms and sum and all this stuff. But I'm telling you how to get rid of, like how to do this thing. So then you can actually try it out and get this. And for the lecture, I was going to do the opposite. I was going to compute these things, so in particular this, so psi with pi, based on this assumption, just to see how this works. So I did the inverse. Like I assume that it holds, and then what is psi x pi y? I'll compute this. And that is a consistency check, right? If that didn't come out right, then that was probably not the answer. It is not a guarantee that this is correct, because there could have been something else that produces the same that doesn't want it. But this computation is simpler and possible to do in the lecture, however, not in 3 minutes, damn it. So now it's either waiting until tomorrow or it's going to get canceled. Canceled altogether. How am I going to fill these 3 minutes? Do you have a question? Please?
Hello?
Mm,
Yeah? Hello? Dr. Klose?
Someone? You could also just go home and start on this homework.
Dr. Klose?
How-
Can you hear me? No?
all these indices. Is this confusing?
Dr. Klose, can you hear me? No?
This is just conceptually like like in part also because it's stuff that we did, I don't know, like a month ago or something, but yeah, I found this lecture a bit challenging.
Yeah, technically it is layer on top of layer on top of layer, right? You have derivatives, you have gamma matrices, you have spinors, you have intercommuting, you have integrals, you have delta function, you have commutator, you have just everything at once. That's why it's good to really practice this. It's not the most important thing in the world, but if you want to, at the end, compute a scattering amplitude, what's the probability of electron positron scattering, then you actually have to go through all of these indexed. But you let me know when I'm too fast and you got lost in the indices or whatever. We'll talk about this. Thank you for today.